Hello, Jovish. How are you?
Fine, thank you for asking.
Yeah, it's nice to see you. Were you able to go with your friend and show the plots and all the insights that we get?
You told me that we have two steps to take the conclusions. Can we go with statistical analysis now?
Yes, let's go and do the statistical analysis and see,
Okay.
what else can we conclude from the statistical analysis.
So here from the graph we get some insights. From statistical analysis we get solid conclusions, right?
Yes, so we
Okay.
will do some tests, some statistical tests, and with some probability we can conclude if the factors affect or not your response. In this part of the statistical analysis, we use a technique called hypothesis testing. So in hypothesis testing, you need to have a hypothesis, as the name implies. So and actually we have two hypotheses, one that we call the null hypothesis and the alternative hypothesis. So 0 is the null hypothesis. Let's imagine that you want to compare if the strength of the prototype is the same when you use different infield density. So here we have mu1 equal mu2. So mu1 is the mean strength when you use a low infield density, in this case 20%, and mu2 when you use 50%. So we make the prototypes, you calculate the mean, and you see if those are the same or not. The alternative hypothesis means that they are the same. So, in this case, the infield density will have a significant effect in your response. We can do this for the layer height, for print speed, and all the interactions. So we can test these hypotheses.
Okay.
So how do we do that? So it's not simply let's take the mean. So we can have the data, we can take the mean. No, it's involved a little more. It's also take into consideration the variability and some other thing. So depending on the experiment that you are using, we have several tests. And here you have some sort of decision tree that you can use when doing an experiment, and is related to how many factors and levels do you have. We have from like the simple one, when you use have one thing that want to compare. Imagine that you have these prototypes that you fabricated with the same condition, and you want to check if the strength it's equal to some value. So you just have one sample compared with a particular value. Then in the middle we have the case of two samples. Imagine that instead of doing the experiment with three factors, you just have one factor, that is the infield density, for example, like the previous one. So you have infield density 20% and 50%. So we have two samples, so we compare those two. So we have like the two sample t or the pair t test, depending if there is a correlation or not between these samples. Then over here we have a more general way to do the analysis when we have two or more groups to compare, and we can have one or two or several factors. Imagine that now you have the same experiment with the infield density, but instead of using 20 and 50, you also have 35%. So you will have like a one factor, three levels. So in that case, we use an analysis called one-way ANOVA. One way means one factor. In general, if you have more, so then we have this ANOVA test. So ANOVA means analysis of variance. So it will, when doing the analysis, it will analyze the variability of the data. The change when you change the factor, but some, in addition, the variability on each group. So for your case, so which one do you think we should use?
So in my case, not sample and not two. I have more than two samples.
Yes.
And I have more than one factor.
Yes.
So it is not one way, it is general one way. We have to go with general ANOVA.
You will use the general ANOVA. Yes, great. So here, for example, you have some plots of what the test will do. So here you see, like two lines. So imagine that you have two, different combination. They follow a distribution. Like in this case, it looks like a normal distribution, and we can see, like the peak these points. So that would be like the mean in some sense. So we want to compare if those two are close together or not. So this test will compare what's the probability that these two peaks are the same or not for each factor that you have. And we may, if we have 3 levels, so you will have like 3 curves and do the comparisons. So to do that, what these statistical methods do is, you have the hypothesis, like the null hypothesis, the alternative hypothesis, then you need to collect the data, so you already have it, you already run the experiment. So then we calculate these test statistics. So the test statistics is just a formula that, depending on the test that you are using, will be how it looks. But it basically summarizes your data with like the mean and the standard deviation for each of the samples, and then with some probability tells you if they are statistically the same or not. So here you have like a distribution, like a plot. So this is like this test statistics. So in your hypothesis, imagine that we have this mu1 equal mu2. So we can, instead of having mu1 equal mu2, so we have mu1 minus mu2. So that's equal to mu1 minus mu2 equals 0. So that's our hypothesis, is that the difference between mu1, our null hypothesis, mu1 minus mu2, is equal to 0. So these test statistics try to mimic that. So the test statistic is based on your null hypothesis is true. So you can see here in this plot, so in the middle,
0.
We have the 0 that is, 1 to see, but of course data has, some sort of variability. So if after you calculate your test statistic, it happens to be in this white region that we call the acceptance region, then we will accept our null hypothesis. If it happens to be on the red section, then we reject, because it's very unlikely, say that you are very far to the right, imagine like 3. So the difference is equal to 3, so we'll say, okay, it's very unlikely that mu1 is equal to mu2, or the strength of the prototype when you use an infill density of 20 versus 50%.
So here we have 2 values, no?
Yes.
One is inside the region, inside the curve.
Yes.
So that we call probability.
Yes.
And one value here in x-axis.
Yes.
So values in x-axis, here in this case we are using t-test.
Yes.
So the t value or t statistic will be in x-axis.
Yes.
And other inside of this curve will be probability.
Yes.
And
yes.
total probability is 1.
Yes, that's correct. So the total probability, so the area under the curve is the probability, as you said, is from 0 to 1, and in the x-axis depends of the distribution that these test statistics follow. In this case, it's a t distribution, and here we are using a 95% confidence level. So this y section, like the area in this y section, is 95%, and the 2 tails is the 5%.
So you are taking 2.5% in both sides, because of your alternative hypothesis is mu2.
Mu2.
If it was like greater than, it will be only one-way test, or less than is one way.
Yes.
So here it's different, not equal to, that's why two-way test.
Yes, it's very good observation, Joey. Yes,
yeah.
Because different could be that one is larger than the other or smaller, so we consider 2 sides.
Different,
but if
different.
it's just different, but if it's smaller or larger, then we go to one side. So when doing this testing and deciding, okay, should I reject or not, so we look at the test statistic and we look, at the t-value in the x-axis, and if it's in this y region, so we accept. However, we have an alternative to do the testing, so we can use something that is called the p-value. Maybe you have heard of this p-value. So the test is equivalent, so you will get exactly the same results, but here, instead of comparing the value of the x-axis as in the previous plot, here we compare the this area under the curve. So is this probability. So we have a confidence level of 5% or the alpha equal as 0.05, then we calculate, the test statistic that here you can see it as the observed value, and then we check, what's the area under the curve from that point to the end. If it's like a two-tail test, so we have it in two sides. So here in the illustration, we just have it in one, but depending on the test, will be different. Then we compare that with the alpha, in this case 0.05. And if alpha is smaller than the p-value, so then, if p-value is smaller than alpha, then we reject the null hypothesis. And this is the general rule that you can use when analyzing the data. Now, let's go to Minitab and do the test so you can see how it looks. So to do the ANOVA, we will go to Stat, and now we will be using this DOE section. Do you remember when we create the experiment, we came to factorial, create factorial design, so we got all the combinations. Now we will go to analyze factorial design. So we will click here, and then you need to select the response. So it will do a test, like independent test for each one, so we can select the 3 at a time. And I recommend you to go and click on graphs and click here where it says 4-in-1. Later we will come back and discuss that plot. Then I will just click OK, and also go to storage and click in residual. So select residual. So we will discuss that later. I will click OK, and these are the results. So you will have, a summary of all the details of the experiment, and one for each of the factors. So this is the one, here we have one, so we can, analyze a little more in deep, and then you can go back and, review the other one. So here you will see, the list of your factors, the one that we call like the main effect, and also the interaction, like the two-way interactions. Then you have a set of values here. One is like the sum of a square, mean squared. Those are calculated to get these test statistics that we need. That in this case is the F value. So the F value is the test statistic, or like the calculated value of the test statistic, and in this case follow an F distribution. Then next we have the p-value. So first we will go to the what we call main effect, like the A, B, and C, just the factors itself. So here, if you look at the p-value, so for layer height 0.00, print speed 0.04, and for the infill density is also 0. So based on the rule that we have, that if p-value is smaller than alpha, we reject the null hypothesis. So what will be the conclusion?
So here we have to reject all the null hypotheses. So layer height 0.1, H0,
like mu2.
Means when I am using this 0.1 layer height and 0.3 layer height, my strength is same.
Yes.
So here p-value is 0, means I have to reject this null hypothesis.
Yes.
That means we have different values.
Yes, so the mean strength of the prototype is different, statistically significant different, if you use a layer height of 0.1 and 0.3. So how about in the infill density, the one that we have with the C?
Okay. So in the case of infill density, we had like 50%. Here also again the same thing, no?
Yes.
So here our null hypothesis is mu1 equal to mu2.
Yes.
That means when I am using this infill density 20, mean is same as mean of when I am using infill density 50.
Yes, like the mean strength.
So here is p-value is 0. That means I have to reject this null hypothesis.
Yes.
That means the means are not same.
They are different, yes. So if we go, if you remember when we were if we look at the main effect plot for the strength, so here we can see how the layer high has a big impact and the infill density also, but not much the print speed. However, here the print speed, the p-value is 0.048. So it means that it also significantly affects, not as much as the other two, but it has a significant impact.
Okay. So if we would have take conclusions only from this graph,
Yes.
we would have missed this conclusion.
Yes,
no?
we have just taken the graph, so we will say that in this case the print speed doesn't have an effect, but we can see from the analysis of variance that it has a significant effect. It's smaller, but it has a significant effect. Now, let's look at the
interactions.
the two-way interaction. So now this other section here. So here, the only p-value that is smaller than alpha is the layer high infill density. The other ones are larger. The first one is 0.4 and the other 0.6. So those are larger. So meaning that they don't have really an interaction. If you remember the interaction plot, so we have the for these two factors that it was a crossing, and for the other was like a parallel plot. So the conclusions are they should be like alike from the plots and the test, like in this case the ANOVA test. However, with the ANOVA test we have this more evidence of the results, and not just we may be missing some things like in the previous one. And we can take a look at the three-way interaction, though it doesn't have a significant really effect. So overall, from the analysis of the ANOVA, the strength, so we can conclude that layer high and infill density are the main factors that affect the strength. Print speed, just it has an effect, but not as much as the other ones. But the interaction between the layer high and the infill density, it's important. So when selecting these optimal settings, so we need to take into consideration the value of the other factors. So we cannot just look individually. And in this way, so you can go and look at the other, two analyses for the print time and also for the softness, roughness. However, before finishing and making all the conclusions, it's important to know that all these statistical tests has some assumptions. So we are doing the test, so we make a model like the regression model to represent the data, then we compare with the true value, and then we have a difference. So that's called the residuals. If we are using Minitab or some other software, it will generate some plots of these residuals. If you remember when we were doing the test, I told you, okay, select the 4-in-1. Okay, so this is how it looks, the 4-in-1 plot. So you can see four plots in one, and these are for the residuals. So we have the two, so those two will help you with the, like test the normality. And the one here, like the fit value versus residual, so that's to check equal variance. And this one here, like the run order, we use it for the independence. So in the normality test, so we have this probability plot. So the red line, it means that the data follow a normal distribution, like theoretically. So you want to look those blue dots that are your residuals are close to the red line. In this case, they look, normal, and we have like the histogram, so it's really look like a normal distribution. Yeah, so it has like this, bell shape. So, not really necessary, need to do a further test. Sometimes if you are not sure if they follow a normal distribution or not, we can do also a normality test. So in this one here, so we look for equal variance. So here you have like 8 groups of points, 1 for each combination. So we want to look, yes, like the variability of all of them is being, similar. And also if we are not sure, so we can do a test. And down here, so we have like the run order versus the residual. So we here don't want to what we are looking is for, some sort of pattern. So if there is a pattern, imagine that when you go further on the experiment, your residuals are growing or getting down. So that means that maybe something was, done, bias. Here,
it is totally random.
Yes, so it goes up and down, so really nothing
Random.
to be worried. So if this looks okay, so then, your conclusions are valid. The error, the residuals follow a normal distribution, check. They are,
These are
they are independent, so just like random here, and then, that's for equal variance. So
in our case, it
Yes.
passed all the tests. That means I did my experiments very well, no? So in case my errors has normal distribution, so what I had to do? I had to go back to my initial experiment and I have to redo all the experiments.
So no, we will look for some alternative techniques. So say that the equal variance was not fulfilled. So we have some techniques called non-parametric test. So they don't have the assumption of normality. Or we look at for a transformation of the data. So it can become like normal or has like equal variance. So if the residuals are not normal or they don't have equal variance, so that doesn't mean that your experiment is wrong. So it may be that for some combinations there is a lot of variability, and from others, the process is very concise, so you always get the same results, but nothing to do with like it was a good experiment or not. In the case of the run order versus the residuals, if we see like a pattern on the results, maybe something was
Not random.
Yeah, not random. It was a little bit biased when doing the experiment. So it's what we can get. But yeah, no, don't worry. So you don't need to run it. Maybe a couple of them you will go and run it again, but not in general. So you will need to look at the residual plot for each of the response, because it could happen that in this case of a strength it looks really good, but for the other two it may not. So I recommend you to go and check the ANOVA table, get your insights, and also check the model assumptions. So here, when I was looking at all the ANOVA tables, so I was taking notes of some of the insights. So please share with your friend which factors have a significant effect on the response or the interaction. But these are independent. You're looking at one response at a time. So the test do not combine the response. And here we have also for softness, roughness, and this is what we look at the strength.
Okay.
So what we are missing now is, since we have 3 responses, so now look which of the settings are best for the 3 together, because here from the insights you can start looking which combinations to use from one and the other.
The first priority is strength. The second priority is the print speed.
Okay, excellent. So the strength, so he wants a good strength, and then the time. So he cares about the time. So I guess then the surface roughness is a little bit less important, because they can cover with some other material or something. Okay, so we will come back and I will show you how to use a tool that is embedded in Minitab that is called Response Optimizer. So in that Response Optimizer, we will put these priorities, and now it will give a combination. Now it will give you the settings.
Optimal settings.
Yeah, the optimal settings, as the name implies. Yeah, the optimal settings, for the 3 responses. So please go and share this with him while we do the other analysis.
Okay, then I will share with the statistical test and conclusions you have drawn. See you next time with response optimizer.
Yes, yeah. See you, Jovish. Nice to see you.
Thank you very much. Bye.
Bye.